Imagine you're hanging out with a computer geek friend and you ask them, so how does this whole CPU thing actually work? Like what is doing all day? Your friend leans back in their chair with a grin, ready to drop some tech knowledge. Good day everyone, my name is Sherwin Cruz from BSCPE 41 and I will discuss on how CPU works.
Picture the CPU as a mastermind of the computer, the conductor of the digital orchestra. It's this tiny chip in the motherboard that's constantly receiving instructions from programs and applications. Think of these instructions as tiny notes on a sheet music. The CPU precious those notes, figures out what they mean, and then tells the rest of the computer what to do. So, if I'm opening a portal, is the CPU telling the screen what pixels to light up? Exactly. It's like a tiny chef telling the kitchen helpers. Chop the onions, slice the tomatoes, mix the butter. But it's not just about the visuals. The CPU also crunches numbers like a super fast calculator. When you edit a video, it's the CPU figuring out how to merge clips, add effects, and make everything running smooth. That's crazy. But what about multiple things at once? Like listening to music or browsing the web. Ah, that's where things get interesting. Most modern CPUs have multiple cores, like having several mini conductors in one orchestra. Each core can handle separate instructions at the same time, like conducting two pieces of music simultaneously. So while you're listening to Spotify, another core might be busy downloading web pages in the background. That makes sense, but what if something needs extra processing power, like a big video game? That's when the CPU can turn up the tempo. It can increase its clock speed, which is like the beat of the music. The faster the clock ticks, the more instructions the CPU can process in a second. It's like a chef working double time to get all these dishes out during a rush hour. Wow, that's way more complex than unimagined. There's definitely more to it, but hopefully you get the gist. The CPU is constantly working behind the scenes, like a tireless conductor, making sure everything in your computer runs smoothly and efficiently.
The CPU, short for Central Processing Unit, is like the brain of the computer, and once you understand how it works, you'll understand the computer as well. Let's remove the cover of the CPU and zoom in to see what happens inside. There are lots of different wires carrying information around the CPU. So let's flip the CPU over and look underneath. You'll see a lot of pins sticking out that allow the CPU to take in information and send it back out. The CPU fits into what's known as the motherboard. The motherboard allows all the components in the computer to connect to each other.
Imagine cracking open a history book of computers, except instead of dusty pages, it's all about the brain of the beast, the CPU. Buckle up, because we're about to trace the epic evolution of this tiny titan. From clunky beginnings to packet powerhouses. From early 1960s, picture giant rooms filled with humming monstrosities like ENIAC. CPUs made of thousands of fragile vacuum tubes. They were slow, power-hungry beasts, but they could crunch basic numbers. Late 60s or 1960s, enter the transistor. These smaller, cooler dudes paved the way for miniaturizations, leading to the 1971 Intel 4004, the world's first commercial microprocessor. This pocket-sized marble fit on a chip and could process 60,000 instructions per second. Think flip phones compared to smartphones. 1970s to 1980s. The race was on. Intel's 8086, 8088 chips powered by early PCs, while Motorola's 68000 brought masses to Apple's Macs. Clock speeds kept climbing, and CPUs learned to juggle multiple tasks, or multitasking. 1990s, Pentium power, Intel upped the ante with 32-bit processing, paved the way for smoother graphics and games like Doom. AMD joined the party and competition kept pushing the limits. From 2000s to 2010s, core galore. CPUs sprouted multiple brains, handling tasks in parallel like a team of chefs. Dual core, quad core, octa-core, and the more the merrier. Today and beyond, we're talking a hyper-threading, specialized instructions for graphics and AI, and even quantum computing peeking over the horizon. It's a never-ending quest for more power, efficiency, and mind-blowing applications. But evolution isn't just about numbers, it's about impact. Internet. CPUs become the engines driving the information age, connecting us across the globe. Mobile revolution. Tiny, efficient CPUs in smartphones put the power of a computer in our pockets. Scientific breakthroughs, from simulating the universe to cracking complex medical problems. CPUs are pushing the boundaries of what's possible. So next time you fire up your laptop or game console, remember the long and fascinating journey of the CPU. It's a testament to human ingenuity and a glimpse into the ever-evolving future of technology. Who knows what mind-blowing things? Alright, gather round friends and let's talk about the GPU, the unsung hero of the graphics world. Think of it as the masters of the CPU brains, the artist, or the engineer. While the CPU crunches numbers and keeps things organized, the GPU is all about creating and dusting visuals we see on our screens. So what does the graphics powerhouse do? Imagine you're playing a game with a bustling city scene. Every building, character, and explosion is made up of millions of tiny triangles. The GPU is tasked with drawing them all on the screen. Fast. It's like having a team of lightning quick painters, each responsible for a specific part of the scene. But the GPU is not just for games. Video editing, rendering the smooth transitions, and adding special effects. That's the GPU working its magic. 3D modeling and animation. It's bringing the characters and objects to life. The GPU's got your back. Machine learning. Training AI models to recognize patterns in images and videos. The GPU's a beast at that too. And how does it work for its magic? Unlike the CPU, which handles tasks one at a time, the GPU is a master of parallel processing. Has hundreds or even thousands of smaller cores, each capable of handling a tiny piece of the graphical workload simultaneously. This lets it tackle complex tasks much faster than the CPU could alone. Think of it like this. CPU. Okay, let's draw this triangle. First, calculate the angles, then the coordinates. Then, slow. GPU, hold my pixels. We'll split this triangle into smaller parts and draw them all at once. Fast and efficient. But GPUs aren't just about speed. They're also about specialized hardware. VRAM dedicated for storing textures and other graphical data, letting the GPU access it quickly. Shaders, programmable mini programs that handle specific tasks like lighting, shadows, and reflections. So next time you're blown away with stunning graphics or smooth animations, remember the GPU, the silent artist behind the scenes. Alright, imagine we're tinkering with the very first computers, back when they looked like something Frankenstein might assemble. We're talking about the SOP 1, a basic yet fascinating machine that lays the foundation for modern computers. It's like dissecting the simplest clockwork toy to understand how timekeeping works. So, the picture the SOP 1, is a tried brain with limited tools. It has 16 memory slots. Think of them as tiny qubits holding instructions or data, each number from 0 to 15. Registers, tiny workbenches like the accumulator where the CPU crunches numbers. Control unit, the conductor telling the different parts what to do based on instructions. Now, onto the operations of the SOP1 secret sauce. LDA or load data. Imagine grabbing an instructions or data from a memory copy and putting it on the accumulator workbench, like fetching a tool from your toolbox. Add USB. Just like it sounds, the CPU adds or subtracts numbers on the accumulator, like using a tiny calculator. Out. Sends the results from the accumulator to the outside world, like displaying it on a light bulb panel. Think of it as showing your finished craft. Halt. Takes a break, stopping the whole operation, like putting down your tools and taking a breather. Here's how it all comes together. You feed the SAP1 program like a series of instructions stored in those memory qubits. The control unit grabs the first instruction, say LDA7 or load data from QB7. The CPU fetches the data from the QB7 and puts it on the accumulator workbench. Maybe the next instruction is add 5. Add the 5 to the accumulator. The CPU does its magic, adding 5 to the stored data. Finally, you might have out or send result. The CPU proudly displays the sum on the light bulb panel. It's all about these simple operations working together to perform basic tasks. Adding two numbers. The SAP1 can handle it. Counting down from 10, just a loop of LDA, sub, and out instructions. Playing a simple melody, use the out operation to control the timing of different tones. The SAP1 might seem crude compared to modern computers, but its operations are the building blocks for the complex instructions our CPU handle today. It's like learning the alphabet before writing a novel. For those who enjoy challenge, imagine programming a computer with only 16 bytes of memory. That's precisely what SAP1 offers, and today we'll explore its unique role in the computer science education. SAP1 is simplified educational computer design to teach fundamental programming concepts. Its constrained architecture forces us to think creatively and appreciate the intricacies of modern systems. Let's dive into its components. A CPU with a programming counter, an accumulator, an instruction register, and a tiny 16-bit of memory. It interacts with the world through basic input and output devices like LEDs and switches. Programming SAP1 involves writing assembly language instructions, each meticulously crafted to fit within memory constraints. It's like writing a story with a limited vocabulary, challenging yet rewarding. Consider a programming that adds two numbers and displays the results on an LED. It demonstrates memory addressings, arithmetic operations, and interactions with hardware core components applicable to all computers. Optimizing code within limited resources is a core challenge. Imagine packing multiple instructions into a single byte using clever bit manipulation techniques. It's like solving a puzzle, fostering ingenuity and problem-solving skills. SAP1's lessons extend beyond its architecture. Memory addressing and instruction cycles are fundamental to our processors. Even the most advanced, it's like learning the alphabet before writing poetry. SAP1 played a pivotal role in shaping computer science education, providing a hands-on platform for grasping fundamental concepts. It's a testament to the ingenuity of early computer pioneers. Despite its simplicity, SAP1 offers a profound learning experience. It solidifies programming fundamentals, cultivates creative problem solving, and provides a historical perspective on the evolution of computing. So I invite you to explore SAP1 further, embrace its challenges, uncover its rewards, and discover the foundational beauty of computer science. From the intricate dance of instructions within the control unit to the raw power of arithmetic computations in the ALU or exploration of the CPU has shed light on the enigmatic yet essential engine driving our digital world. We've witnessed the remarkable evolution of processors from the humble beginnings of single-core giants to the modern marvels of multi-core marvels, each generation pushing the boundaries of performance and efficiency. However, the landscape of computing extends beyond the traditional CPU. We've glimpsed the specialized powers of GPUs, their parallel processing powers, tackling the demands of graphics and machine learning within the unmatched efficiency. This glimpse into the device or diverse ecosystem of processors leave us with a newfound appreciation for the intricate interplay between hardware and software, empowering our digital experiences. Yet, the journey doesn't end at the physical hardware. We've delved into the world of SAP1, a simplified platform that unlocks the fundamentals of programming. Through its limited resources and assembly language commands, it becomes a playground for understanding core concepts like memory addressings, instruction cycles, and basic operations. This first-hand encounter with coding's foundational building blocks reinforces the crucial role of software in orchestrating the symphony of hardware. Looking ahead, the future of computing promises even more exciting horizons. As Moore's law approaches physical limitations, the focus shifts towards innovative architectures, specialized processors, and advancements in software optimization. The quest for ever greater performance and efficiency continues, fueled by relentless curiosity and groundbreaking discoveries. Therefore, this exploration of CPUs, GPUs, and SAP1 programming serve as a springboard for further inquiry. It leaves us with a newfound appreciation for the complex dance of hardware and software, the intricate workings of the digital brain, and the boundless possibilities that lie ahead in the realm of computing. We stand at the threshold of a future where processors become increasingly specialized, efficient, and interconnected, pushing the boundaries of what's possible. These understandings of the fundamental building blocks, from SAP1's basic instructions to the intricate dances of modern CPUs and GPUs, equip us to actively participate in shaping this exciting future. So let us remain curious, innovative, and driven by passion to unlock the full potential of the digital world that surrounds us. Thank you very much. My name again is Sherwin Cruz from BSCPE 41.